Now we'll study regression analysis, which is a part of machine learning techniques. See this recall. It is a review of section 6.5, the last section. A is an n by n metric, and B is an Rm. The least squares solution of Ax equals B is a vector x hat in Rn such that the norm between here B and Ax is minimized with x hat. The set of least squares solutions of the linear system coincides with the non-empty set of solutions of the normal equations. So to solve the least squares problem, and we may use the method of normal equations. The normal equations have a unique solution if and only if the columns of A are linearly independent. So when the columns of A are linearly independent, then that is invertible, and we can define the pseudo inverse of A. So x hat will be pseudo inverse of A times B. Right? Now, once A has linearly independent columns, then we can get QR factorization with R of a triangular metric having positive entries along the diagonal. Then for every choice of B, the equation Ax equals B has a unique least square solution given by that equation. By using the property Q transpose Q is identity, the pseudo inverse is simplified to get that one. So we reach this conclusion. Okay, here we have a subsection, regression line. Now, we assume we have the data points, blue dots, and let's try to find the regression line, the best fitting line. Okay, here we have definition. Suppose a set of experimental data points are given as here, and x1, y1, there is a point and another point, and there are m points. So these are m points. Each dot is a point, such that the graph is close to a line. So once you look at the scatter plot of bullet points, then it looks like a line. So we determine a line y equals beta 0 plus beta 1x that is as close as possible to the given points. So that is a kind of a best fitting line. This line is called the least squares line, and also it is also called regression line of y on x, and beta 0, beta 1 are called regression coefficients. In solving the problem, the target is to find that two coefficients. Okay. To get the coefficients, now we consider here this remark. Consider a least squares model of the form y equals beta 0 plus beta 1x for a given data set xi, yi, I is from 1 to m. If we are using first point I is 1, then here xi, yi But once we assume that beta 0, beta 1 are already known, then this will make a predicted value along the line. So the value will be on the line. Now, this is the observed y value given in the data set. So it's not the same, but we write down in this way. And for second point, we have this equation and so on, so that for the last point, we have that equation. These n equations can be written in this metric vector form, and x is, and the first column is all 1, and the second column is collection of x values, x coordinates, and beta is the same as the coefficients beta 0, beta 1, and y is the collection of y coordinates. Now we have to find least squares solution, so that for this linear system, already we know that the least square solution of this system are the same as the solutions of the normal equations. Right? So from here, we try to get now normal equation. Once the points are obtained, more than 2 points, then these two columns must be linearly independent, so that x transpose x must be invertible, and we can get the coefficients, the target unknown, from that equation. Here, x is called the design metric, and beta is the parameter vector, and y is the observation vector. Okay, let's try to solve this problem. Find the equation y equals beta 0 plus beta 1x of least squares line that best fits the given data points. Okay, once data is given, then you may write down the data in table format. For example, x and y here, and then we have x is from -1, 0, and 1 and 2, and y values are from 0, 1, 0, 1, 2, 4, right? Okay, we have that x and y values for this one, and x, the information metric, is all 1 for 4 points in the beginning, and collection of x values -1, 0, 1, and 2. And right side vector, y here, the observation vector is collection of y values. That is, we have from here 0, 1, 2, 4. Right? Okay. Now we have to organize x transpose x and now x transpose y. Let's do it here. X transpose x. That is, rather than writing x transpose, okay, after taking x transpose, first row, the first column is the same as this first column dot product with itself. Okay, that is 4. Now, want to position, there is dot product of these two columns, -1, 1, and 2. It's symmetric, so it must be 2. Now, dot product of this second column with itself is 1 plus 1 plus 4. That is a 6. Right? And how about x transpose y? dot product with this one and that one, all summation is 7. That's now, okay, 0, 0, and 2 plus 6. It's 2 plus 8. Okay, this 8 and 2, so that must be 10. So we have to find beta by solving this metric times beta is the right side. We can get it easily. Here, we may try to use elementary row operations. We write down this one on the top with scaled by 2. Then it's 1, 3, 5. And then, now that is 4, 2, 7. Okay, from here, 4 times subtraction. 4 times subtraction will make this one 0. 4 times subtraction, so minus 10. 4 times subtraction is 20 is subtracted. So that is now minus 13. Okay, so that's 1. Okay, we divide by, okay, we multiply 1 over 10 minus 1 over 10, then that will become 0 and 1 and 1.23. So 3 times subtraction will make 1, 0. 3 times subtraction, 3.9 is subtracted, which means that there's 1.1. And then this one is 0, 1, 1.23. That means beta 0 is 1.1, beta 1 is 1.3. So the final model we found is y equal 1.1 plus 1.3 x. That's the final answer, right? Okay, now we look at the system in this way. Here, for linear regression, linear line, here we have always like the x transpose x, then this is x transpose and that is x, and this dot product will make m, and here that dot product will make a summation of xi. Of course that must be the same, and these two dot product will make a summation of xi squared. And for right side, here x transpose y, the first entry must be summation of yi, second one must be summation of xi, yi. So we have this metric. For this one, we may try to use this formula. Okay, let's try to do that. Now, again, if you try to display the data points in table, then sometimes is much better. So this time we'll try to make vertical table. Okay, let's try to write down xy, and then either way you can use vertical or horizontal. Is x is changing 0, 1, 2, 3. Okay, that is 0, 1, 2, 3. Y values are 1, 1. Okay, here that is 1, 1, 2, 2. Okay, we have the data displayed. Okay, for the metric m, there are 4, so that is 4. And then summation of xi, which is 6, again here. Now xi squared, 1, 4, 9, so that's 14, right? And beta, and right side is a summation of yi, that is 6, right? That is 6, and summation of xi, yi. Okay, that multiplication is 0, 1, now 4 and 6. 1 plus 4 plus 6, which is 11. Okay, so we have to find the solution for that one. Now again, with the augmented method, we can finish it. Okay, divide by 2, so that'll be 2, 3, 3, and there's 6, 14, and 11. From this augmented metric, we can get, okay, 2, 3, 3, and 3 times subtraction will make a 0. 3 times subtraction will make a 5. This is 9, so that is a 5. 3 times subtraction will make a 2. Okay. Now from here, we'll scale, divide the second row by 5. Then that will be here 0 and 1, and there's 0.4. Right? Okay. Now from here, we try to subtract 3 times of the second row, then 2, 0, 3 times 1.2 is subtracted, so that the middle part is 1.8, and 0, 1, and 0.4. That means that here the first component in beta is divided by 2, 0.9 and 0.4, and that is the second one. So the final model we found is here y equal, and that is 0.9 plus 0.4x, right? We can check by using some graph. Okay, let's try to visualize the data points and the model we found for this problem. Okay, here we have now x-axis and y-axis. Here is from 0, 1, 2, 3. Now x is 0, then y equal 1. And again, 1 and 1 here. And then x is 2, then the value is 2. And again, one more time, 2 here. Right? Okay, that's the data points. And this one is slope 0.4 and passing here 0.9. Let's try to use red pen. So 0.9 must be around here. And then slope is 0.4, so that it looks like a passing like that here, like that, right? So it's quite reasonable, the least squares line. And that is best fitting line. So, and the least squares error is minimized along with that line. Okay. Okay. We'll continue in the second part. Thank you.